Hello everyone, welcome to my presentation. My name is Oana Ciobotaru. I am part of the Pegasus R&D team, and I have actually a couple of slides here about our work and our team. So Pegasus' mission is to make Ethereum enterprise ready, and we have a few efforts in that direction: building Ethereum enterprise, building production-ready technology, and driving next-generation innovation. In order to achieve that, there are teams in place supporting that. So there is a product team, an R&D team, which I'm part of, and a standards team. And I'm more than welcoming you to our website to check our work there. And to kick it off, today I would like to talk about zero-knowledge proofs. So I would like to give a introductory talk. I'm not sure how much of the slides I can cover, but basically in the first part, I will give semi-formal definitions to zero-knowledge proofs. Then I would like to cover the Schnorr protocol with examples to everything in the proofs. And then, if there is time, I would like to present a transformation of a circuit to a QAP representation, which is one important step for achieving zero-knowledge proofs in the SNARK framework. So to begin with, two motivating examples. First, we have verifiable computation, where as a setup, a client C would like to compute a function f for a large value x, and where f is also considered expensive. So let's say this client, for example, is using a mobile phone, so he would like to delegate a server to perform the computation for him. So what happens is that the server performs this computation, returns f of x, but now how can C check that computation was done correctly? The first solution is to simply have the client recompute everything, but, well, that's beyond the point. So a better solution is for the client to encrypt x and f using fully homomorphic encryption, and for the server to perform the computation on the encrypted value and to return an encryption of f of x, which C can decrypt and retrieve the necessary value. Another motivating example that occurs in real life. So we are talking about privacy on the blockchain. And for example, for regulatory purposes, we would like to have two properties. We would like A and B to be able to perform private transactions. Let's say A and B are two financial institutions, while also ensuring that double spending doesn't occur. So first solution is privacy via quorum, but that doesn't support protection against double spending. So a better solution is for A to prove that she has a positive amount of coins, her transaction is well formed. This depends on blockchain, and the input value on A's transaction is at least as high as the output value, so the amount that she pays to B. And she would have to perform a proof that her input has all these properties without giving any further bits of information to B regarding that. So all of this is done with zero-knowledge proofs. And this is the better solution that that was written on the previous slide. So how does this work? How does this better solution work? So we take any reasonably complex protocol, and we want to ensure that participants don't misbehave. How do we do that? Basically, after every step, one has to prove that he or she performed the step correctly. But on top of that, the proof must not reveal any extra knowledge on the secrets that the participants have. So both of these goals are achieved using zero-knowledge proofs, or ZKP proofs, or ZKP. So let's see. Okay, we have zero-knowledge proofs. In theory, they existed. Cryptographers have been working on them for 30, 40 years already. But how about practice? One current efficient solution is zk-SNARK. It has been created at least since 2012. A first implementation was via the Pinocchio protocol, and right now it's actually used in practice by Zcash, and there are it's front end and back end. There are various front ends and back ends to allow creation of zero-knowledge proofs in the zk-SNARK framework. For example, we have Socrates, but many more. So the outline of the talk, as I said, I would like to give some definitions in the first part, and then, time permitting, I would like to present a transformation of a circuit into a quadratic arithmetic problem. So I will start with the zero-knowledge proof game. So assume I would like to convince somebody who's colorblind that I know the difference between red and green. So I would take 2 billiard balls, one red, one green. I would give it to this person, and I would let this person, my friend, let's say, shuffle them behind his or her back, and then allow her or him to present in front of me, and I would say whether she or he switched them behind the back or not. Obviously, if the two balls have different colors, I'm able always to tell whether there was a switch or not. So I will be correct with probability 1. But if the balls have the same color, obviously I will be able to tell the difference only half of the time. Now, if we repeat this a few times after, let's say, k iteration, the probability that I am successful decreases exponentially, so becomes only 1 to the k. So after, let's say, 100 iteration, or maybe even 10 iteration, the friend is convinced that if I'm always right, the friend is convinced that can't be that I'm right just because of luck. There is a very little chance that I am right just because of luck. It means that the balls are indeed different colors, and I can distinguish red from green. So that's an example. And some useful computer science language that we are going to use. We are going to talk about NP language. That's basically the language of all pairs, witness and witness W and instance X, for which there is an accepting polynomial, for which there is an algorithm running in polynomial time that accepts that X. Also, we have the notion of NP-complete language, which is basically a subpart of a subset of the NP languages. And these are like special NP problems for which there is a reduction from any, for which there is a polynomial reduction from any other NP problem or NP language. Good. So now I would like to focus on zero-knowledge proof definition. Zero-knowledge proofs are, first of all, interactive proofs. So this means that they have completeness and soundness. Zero-knowledge interactive proofs deal with two parties. They are traditionally called prover and verifier. The prover would like to convince the verifier that he knows, or would like to convince the verifier of the validity of a certain statement. So there are two security properties that interactive proofs have to have. First of all, there is completeness. An honest prover can always convince an honest verifier about a correct statement. We say with very high probability. It can be because it can be repeated many times, so it's exponentially close to 1, this probability. So that's completeness. Soundness, it's a property of the verifier. This basically ensures that no malicious prover running even in super polynomial time cannot convince of an honest verifier of an incorrect statement besides a very small probability. So here it's very important the fact that P does not necessarily have to run in polynomial time. As we'll see next, there are some simple theoretical or academic differences when P runs in polynomial time or in super polynomial time. We'll talk about this in a bit. So far we had completeness that ensures everything makes sense for an honest prover and an honest verifier. Then we had soundness that that ensures a honest verifier is protected against a dishonest prover. So what remains is the third case, when a honest prover is protected against a potentially malicious verifier. And this is ensured via a zero-knowledge property. So the zero-knowledge property is written here. Given a common input x with honest prover P, whatever V star, potentially malicious, running in polynomial time may calculate on from the interaction with P can also be calculated on X alone. So this, if you study crypto papers, this means that the interaction can be simulated. Let's see for a second why this makes sense. So on one hand, we have the interaction between the prover and the verifier. The prover may or may not have the witness associated with X. Obviously, if the prover has the witness, of course, it can convince the verifier and the statement is indeed true. The problem is when the prover, the problem is here when sorry, there is no such witness. In fact, I will take that back. So the problem here is, in the ideal world, when we have just X alone, and we want to compute anything from that, obviously there is no secret involved, so no secret can be leaked. So if the interaction between the prover and the verifier is indistinguishable from the interaction of somebody trying to compute anything from X alone, it means that the interaction in the first place did not leak anything about the secret, because in the second place there was no secret, it was just X. So that's the property, that's the zero-knowledge property. Okay. Now, in practice, what happens, we have something a bit stronger than zero-knowledge proofs. We have something called zero-knowledge proofs of knowledge. And here, basically, zero-knowledge proofs of knowledge are strengthening the soundness property. So remember, the soundness property was protecting the verifier. So we say zero knowledge proof is a zero knowledge proof of knowledge if it's obviously zero knowledge proof first, and then if P can make V accept, there is a knowledge extractor that, given access to P, and for any instance of X in the language, can extract a witness. This basically says that whenever P can convince V to accept, somebody can extract a witness from P. So this means that a witness exists, even though it's not written per se on the tapes of the tapes of the machine P, but it can be extracted, computed from whatever P knows. Okay, so I would like to present now as a case study Schnorr protocol, which is a very simple example of zero knowledge proof of knowledge. So the setup is quite straightforward. We have P and Q prime such that Q divides P minus 1. GQ is the unique subgroup of ZP star of order Q. We have G a generator of GQ, and here the prover has like the public parameters are GQ. Actually, the public parameters is exactly at the intersection of what the prover and the verifier knows, and this is GQ, G, and H. And the secret value here is actually this witness W. And this is part of the public value H, because H equals G to the W. So basically the witness is incorporated in this H, which is public. And now the prover would like to prove to the verifier that he knows W, which in this case is called the discrete logarithm of H with respect to G. And this is possible in a three-step protocol, also called a sigma protocol, which in this case has a very special name called Schnorr, because obviously it was created by Schnorr. So how this goes? First, the prover samples at random from GQ a value R and hides it in the exponent in the exponent of G, so creates G to the R, sends it to the verifier. Now the verifier works with a random value, so basically creates a random challenge from ZQ and sends it back to the prover, and that's the only thing that the verifier sends back. And then the prover computes again things in the exponent. So he computes. So this time, the first time he was basically sending some sort of commitment, and now he works with the value created by the verifier, and he works with the previous value that he created. So basically he camouflages his witness W with the challenge that the verifier sent and with the randomness that he created before. So all of this is basically something that happens in the exponent, and he sends this back to the verifier. Now the verifier performs this check, and if this check holds, this is the meaning of this equality followed by the question mark. If this check holds, then the verifier is satisfied. This can be repeated. It's an interactive process and can be repeated a few times. And the takeaway message on this slide is that completeness holds. So if everybody is honest here, prover, verifier, if the prover indeed has the witness and everything was computed correctly with the correct randomness, and if the verifier is honest with the correct randomness, this check really passes. That is very easy to see. So that's completeness. If everybody is honest, the verifier accepts. Now, there are two more properties to ensure. One is soundness, and the other one is zero knowledge. In case of Schnorr protocol, we have actually a variation of soundness, which is called special soundness, which also implies proof of knowledge. So special soundness is the following property. Given two accepting conversations, one can compute, given two accepting conversations between the prover and the verifier, such that the statement is the same in both conversations, but, the statement is the same, so X is the same in both conversations, but, and also the initial value that the verifier sends is the same in both conversations, but from there on, there are two different challenges that the verifier sends. So if such two conversations are given to us, then one can compute the witness W. And this is again very easy to see, because assume you have two such accepting conversations. According to this computation here, one can compute W. So what does this tell us? That if there is a machine here that basically, if there is a machine here that basically can have the prover, can interact with the prover and can rewind the prover such that it will always make the prover rewind to the first initial statement and then accept two different challenges from the verifier, then that machine can compute such a W. So this means that the prover indeed knows such a witness. So the prover is honest. So whenever such conversations can be obtained, it means that the prover was honest and soundness has been fulfilled.
I have a question, sorry.
Yes, please.
From a very naive outsider perspective, this seems undesirable, but you seem to suggest that it's not, because surely you don't want to leak W. Isn't W the secret that the prover holds? So the fact that you can rewind and do this differential analysis and then the verifier can calculate W, that doesn't seem like a property I want of my protocol.
That's a very valid and fair point. There are two things to that. Schnorr protocol is not used exactly like that in real life, first of all. And then second thing, in reality, the prover would know that he's being rewinded. So, okay, there is this machine that I said that is rewinding the prover. This exists only in the security proof. Because in reality, all we have, this is a great question, so I'll try to elaborate on that. In reality, we have just the prover and the verifier, and the prover would know if he's being rewinded. He would not allow himself to be rewinded. But now, this is the real world, and in ideal world, all we have in the security proof, in order to prove security, we'll have a machine, the extractor, that basically has a access to the prover and can do anything to it, can set up the random bits, can rewind it, can do anything. So we will say if the interaction in the real world is indistinguishable from the interaction in the ideal world, then, or actually in this case, if given access to the prover in the ideal world for this ideal extractor, if the extractor can extract W, it means it exists, but in the ideal world. So, and if the interaction between the prover and the verifier in the real world is indistinguishable from that of in the ideal world, then obviously the two worlds are the same, and if in one world I can extract the witness, it means it exists in the other world as well, if that makes sense. Yes.
So is this saying that if the prover... Sorry, can you hear me? I don't know if this is working. So is this saying that if the prover can execute twice on the same W with the same A and the same response from the verifier...
Different responses from the verifier.
C is the... Sorry, different C. So different response from the verifier, but the same A.
Yeah.
The only way that can happen is if W is the same, and that means the prover has W.
Yes.
Okay.
Yes. So basically, here, if you go and read like crypto papers and like the actual formal definition, which I didn't give here because I was wanting more to give the example of how it works in reality, you will say that the knowledge, the bound for the proof of knowledge or the knowledge soundness, it's actually 1 over the, let me see, I think the size of ZQ. So because only you can basically, as a prover, you cannot convince the verifier more than with probability 1 over the size of this ZQ. Because if the verifier tries a different challenge, for sure it will know you have a in this ideal world. If you try this in ideal world, for sure you can extract the witness. So you can't misbehave more than with a certain probability. So this gives you basically a bound on the soundness. And again, remember here, the extractor is only in the ideal world, is not in the real world. It's a security construct. Okay. And the final bit, we are also interested to protect the prover here. So this is a bit of a funny notion because it says Schnorr protocol is honest verifier zero knowledge, but we want to protect the prover, and we consider already the verifier to be honest. So what is in there? The thing is, this looks like a weak notion. The thing is, cryptographers use this weak notion to very easily, from here, with just another step, build a fully, full zero knowledge protocol. So even though this looks a bit foolish, this is actually very useful for crypto proofs. So Schnorr protocol, as I said, is honest verifier zero knowledge. What does this mean? That if the prover interacts with if an honest prover interacts with an honest verifier that always chooses his random bits as it should, meaning uniformly at random from this set, then the verifier doesn't learn anything about the secret of the prover. Yeah. And doesn't learn anything, again, translates into a cryptography game where in the real world we have the interaction between these two parties, prover and verifier, as written here in the slide. And in the ideal world, now we have a different machine, is not the extractor, is the simulator. And the simulator, what he tries to do is just give an X, which in this case is this public, are all these public values, tries to obtain similarly distributed outcome as the outcome of this interaction, but again, just from the public values. So if from the public values you can obtain the same, we have basically the same distribution as the distribution of messages here, and obviously here there was no secret involved, it means that in this interaction, the verifier didn't learn anything about the secret. Does this make sense?
Actually, why is there a verifier interaction at all? Because the verifier doesn't have anything secret or special that they can do in any case.
Remember when we were talking about the, I mean, this is a good question. when we were talking about this verifiable computation, so the verifier would be somebody who has a phone and would like to perform a heavy computation but doesn't have the resources. So would send probably something like that. This is the X. Together with another, like a function, a very complicated function, and would ask somebody, like, let's say, would like to have some statistics on some heavy, like, medical records, right? But you would just have a phone or not a very powerful computer, and you get the computation back. So the verifier will get the computation back, like something like that, yeah. But he would like to check that indeed the computation is what he asked for. Okay. Well, in that particular case, also to make it, like, to explain the example to the end, also the prover who owns the medical records would not want medical records to be leaked besides, let's say, some statistics of the medical records. So in that case, you would want a zero knowledge proof. Okay, so that concludes the Schnorr protocol demonstration. Now, there are differences, as we talked already about, between proof of knowledge and zero knowledge. On one side, for proof of knowledge, you would use an extractor who's allowed to rewind the prover. For zero knowledge, you use a simulator who does some internal tricks to come up with a proof without a witness. Plus, he can rewind the verifier. So these machines have different powers and capabilities. And don't forget, these machines, even though they look like they contradict each other, they work in the ideal world. There is nothing, they don't work in the real world. They are just a security construct that allow researchers to say, if such a machine exists and does such and such things in the ideal world, it means in my real world, I have such a security property. And you can read more about that, for example, on Stack Exchange on the link provided. Now, we talked about honest verifier zero knowledge, and we saw how this can be done with 3 rounds of communication. Besides some trivial NP languages, there is no zero knowledge proof with 3 rounds of communication. And the example that we saw can be transformed very easily with just a commitment in the beginning into a full zero knowledge proof for some languages. So basically, what I want to say with this, with just 4 rounds of communication, you can have full zero knowledge proofs for certain NP languages, which is quite nice. But again, we have interaction here. I'm not sure how much time I have left. 5 minutes. Thank you. Okay, so just to summarize a bit on that, the good news is there exist zero knowledge proofs for any NP language if unbreakable encryption exists. That's a well-known result since the 90s. In fact, people were working in theory with zero knowledge proofs, but they have been very inefficient for a very long time. The good news is that has changed currently. Now, if you want to construct a zero knowledge proof for a very specific language, what you would do, you take the following route. You would find an NP-complete language which allows for an efficient zero knowledge proof or zero knowledge proof of knowledge, and build that. And then you transform your problem. If it is an NP statement, you will transform your problem, you will reduce it to this NP-complete language. And this can be done in polynomial time. So overall, combining the 2 steps, you get a zero knowledge proof for your specific NP language. Now that's how people go about things. And then another problem that arises, so we saw there we have 4 rounds of interaction. What people would like usually to have, it's a non-interactive proof where simply the prover posts a proof and everybody can be a verifier and everybody can check it. This requires more technicality, so it can be done usually with either a common reference string or a trusted setup, or with a random oracle model. The random oracle model is not always available, so sometimes people, the only way to obtain non-interactive zero-knowledge proofs is via this CRS or common reference string. Okay, so maybe like to conclude, right now there are a few types of zero-knowledge proofs that are known: ZK snarks, ZK starks, and bullet proofs. They have different pros and cons. So some are efficient with respect to the size of the proof. For example, ZK snarks. ZK starks are very efficient with respect to the verification time, and bullet proofs are very efficient when they are specialized for range proofs. Normally there would be a second part to my talk where I would start describing the process of obtaining a snark. Yeah, so I wanted to, in the second part of the talk, I wanted to transform a problem into like a circuit into a quadratic arithmetic problem, but that is, well, maybe as homework, and I will leave the slides and you can enjoy them. Any questions?
Yeah, really interesting, thank you. How close are Ethereum to launching like an equivalent?
There have been demos. That's a good question. There have been demos of like something equivalent to Zcash on Ethereum, and I think currently as a benchmark, that's about like 70 transactions per second. So that is, but more like a, as I said, as a proof of concept, so that exists. We have done that in our team, actually. One of my colleagues, Gautam, had done that.
Was he at DevCon in Prague?
No.
Any questions? Any more questions?
Where is it possible to see these slides later to do the homework? I'm very keen on that.
I can, like, I don't know, I can provide them.
Do we have a way, Oleg, to share these slides? Okay.
So they'll go on the skills matter probably.
Okay.
So
Sounds good.
I'm very happy to
Just put a link on Meetup.
to share
We
them.
will share the slides for those of you who like
There are
this kind of
references
stuff.
as well, and there are more definitions and everything.
Yeah, just share it with me and then I'll.
No problem. Okay.
Any more questions? Yeah, I had one.
Of course.
Yeah, so this is related to one of your very first slides when you were, I think it was one of the first or the second,
Okay.
and when you were sending
Sorry
to...
about this.
Yeah.
Okay. Here?
Yeah, here, this one. I didn't quite understand why this, the second solution is better when we are receiving an encrypted response, because I will still need to, once I decrypt the FWX, I still need to compute that and verify that the work was done, no? So
that is correct. So I say here, I hope I didn't make a mistake, I say here S sends this result, which is encrypted, which also protects basically C, protects C from allowing S to know what X is and what F is. And also S proves to C that res was computed correctly. This is where the zero knowledge part comes in. So S would send the value back, the server would send the value back, which is something like that, and would also send a zero knowledge proof. This is what it meant, what was meant, but was obviously before introducing zero knowledge proof, so I didn't want to say. But this is has to be there. So S has to send the result and the proof. And C will look at the proof and be the verifier in this interaction and verify that the proof is correct.
Just on that though, that's you talk about them both being zero knowledge, but this type of homomorphic encryption is quite different to what you described just now, I guess, in the... is that, or is it the same thing? I don't know.
It was an example here. I was not talking about homomorphic encryption, that's correct. It was just an example where zero knowledge proofs are used in reality, or can be used. Well, fully homomorphic encryption is far from actually reality right now. It doesn't really exist besides paper. But
okay.
I was just explaining an example where such proofs, zero knowledge proofs, would be very useful.
Great. Thank you very much, Oana.